Bonjour tout le monde. Donc, on va commencer le séminaire. Alors, aujourd'hui, on est avec Léonard Seydoux de l'IPGP. Ça va, le voyage s'est bien passé?
Ça va.
Donc, de l'autre côté de la rue. Donc, l'Institut de physique du globe de Paris. Donc, Léo est passé par d'Alembert en M2, je crois, par l'équipe LAM. Ensuite, il a fait sa thèse à l'IPGP, postdoc à Grenoble, à
Ouais.
ISTER et à Boston, c'est ça. Et donc maintenant, Léo est en poste à l'IPGP et il étudie donc la sismologie et notamment le traitement de données et de l'IA.
Mm.
Voilà. Et donc,
Merci. Okay, merci. So should I switch in English or? Yes, I should. Okay, I will do it in English then. Thank you, Benoit, and thanks for the invitation. So as you said, I was here a while ago. It was a little while ago, maybe 15 years, I don't remember. And so since then, I moved to seismology. So I'm now working at IPGP, as you said, on geophysics. So the goal of this presentation is just to make a review of what we're doing there and maybe also start discussing about things we could do all together if you're interested. So this is the person that these are the person I've been working with on these kind of topics. And the topic is basically how do we use AI to dive into complex geophysical data and infer knowledge automatically out of it. So the main motivation of this work is basically it's a common goal for many people at IPGP. The goal is to better understand these large catastrophic natural hazards that we can observe from time to time, illustrated here with a large earthquake and tsunami in Japan. And this is also a large volcanic eruption that occurred on a large volcano, the Merapi volcano in Indonesia. So the idea is to improve our knowledge of the alea, that is the hazards that are related to this kind of large geological systems. So just to narrow a bit the focus, I will speak only about earthquakes today, but we can also speak about that later. So I was asked to do a gentle introduction. I did my best. You tell me if it's okay. And if it's not, you just ask me a question. It's perfectly okay. So what you see here is a subduction context. So basically, you have to imagine that you have a plate that is subducting beneath another plate. This is a continental plate, and this is most of the time an oceanic plate. This forcing of the subduction is due to tectonic forces in general. So there is basically the creation of this plate in the middle of the ocean, mantelic convection and things like that. And basically, the color scale here indicates the coupling between the two plates. Most of the time, the coupling is quite high here, which means that the continental plate is being pushed by compression towards a given direction. So here it's towards the right of the drawing. And this square here is a symbol that represents a GNSS sensor that you can use to measure displacement. So if you measure the displacement of a continental plate over long duration, so this is a schematic drawing, of course, most of the time you will observe that there is a loading, which means that basically there is an accumulation of energy within the continental crust. So you have a motion that is going to be like eastward. And suddenly, sometimes you have a release of energy when accumulation of the stress is not possible anymore. There is a rapid slip that occurs at the plate interface, and there is a rapid motion in the opposite direction of the subduction. So if you would observe that on a GPS data, you will observe a very rapid slip. And this is what causes seismic waves to be radiated and cause damage to the population. So this seismic slip here can occur on the course of seconds, hundreds of seconds, depending on the size of the earthquake. And it's followed by the rapid after slip here, which is basically a moment where there is a reorganization of the stress and a new coupling is going to occur at the subduction interface. So here on my drawing, I said, okay, all the energy accumulated was released. Of course, it's not always the case. And this after slip is where you have a lot of aftershocks recorded by seismometers. And at some point, you will couple again the two plates and you start a new seismic cycle by new loading, followed by a series of earthquakes. So this is a very naive model, just to understand what's happening there. And of course, if everything behaves this way, there is no a real difficulty in predicting the next earthquake. It will be sort of like regular, and you can anticipate well when is going to be the next one. Of course, it's not what happens, and I will explain why. But there is a small difficulty we need to understand, that the observation we have nowadays are limited in temporal duration. So this is a scheme that represents how we monitor this kind of structure nowadays. We have a bunch of satellite data that can basically deliver information about the deformation. We use GNSS, GPS, also INSAR to measure this deformation. We also have terrestrial instruments like seismometers, tiltmeters, critmeters. We measure with that the deformation and dynamic of deformation. Also, we have knowledge about the rock mechanics and things like that. But this observation, they span only a decade, which means that what we are saying here is inferred from modeling, is also inferred from paleo observations. And we have few examples of large earthquakes that were digitally recorded like that. So just for the illustration here, I'm showing the GNSS displacement that was recording during the magnitude, so it was a magnitude 8.8 earthquake in Chile. So this is probably the third largest earthquake ever recorded by the modern instrumentation. What you see here is the eastward displacement, so the subduction occurs like that. So you have this plate that is subducting beneath this one. The GPS sensor is located somewhere here, and you can see that most of the time you're loading, and suddenly you have the strong co-seismic slip that is recorded by the GNSS, followed by the afterslip. And we're still in the period of the afterslip, 15 years later, which means that the coupling between the plate is not yet recovered. So we're still sleeping a bit. So this is basically on the scheme, it would correspond to that period, basically. And here, so the color scale indicates what we think was the slip at depth on the plate interface. So in order to do that, you need to make assumption on where is located the plate interface. You need to make assumption on the rheology. You have several GPS sensors that observe this slip, and you try to find the slip at depth that best explain the slip observed on the GNSS. And so you can see that over this area, this is probably the best model at the time, because we had only a few sensors. Some places hosted a slip of about 20 meters on the course of seconds on areas that cover several hundreds of kilometers. So it's a colossal earthquake. Yes? Because it's what occurs exactly during the main slip. We disregard the after slip. Okay. So this slip is only explained by a very small time period on GNSS. So co-seismic during the earthquake, after slip after the main shock. Yeah. So, okay, nowadays we have much more instruments located in this same area. And what we do, we use machine learning, deep learning to better detect and locate earthquakes. So what I've been showing so far is just a measurement of displacement based on GNSS. Now we use also seismometers to detect these small earthquakes that occur after the main earthquake. So these are aftershocks. And these small aftershocks, they can be of very small magnitude. They're hard to detect with classical techniques. Up to 2015, the best detection of earthquake we could make was based on human detection. It's not really scalable if you want to detect many earthquakes, but so the peaking was manual. So this is a waveform of an earthquake. You see basically two waves arriving, because we are on an elastic Earth at the first order. We have longitudinal waves and transverse waves, so the P and S waves. And so by picking accurately these two waves at several sensors, we can locate quite accurately an earthquake in the medium. So basically, this picking is nowadays made with deep learning. So we trained neural networks to recognize P and S waves in the data. We automate the detection on many sensors. And then we try to find the sources that best explain the picking that we did. And we need to do assumptions also here. We need to have an idea of what is the velocity of the different types of waves. And we test different sources, trying to match the observations. And if we do that on many earthquakes, this is the kind of catalog we can make. So this is the catalog of the aftershocks of the Maule earthquakes, revisited from what we had before. So with the deep learning, we can detect about 10 times more earthquakes with a much lower magnitude. And what is interesting to do with that is to better understand exactly where the slip occurred, okay? So if this is an image of the co-seismic slip, this is going to be kind of an image of the after slip. And it gives information about the dynamics of the reorganization of the stress after the earthquakes. It also gives us an information on exactly where the slip stopped to better understand how the loading was made on the neighboring sites, okay? Because if you have a big slip here, of course, the neighboring sites are going to be overloaded. So you need to take that into account to better understand what is the seismic hazard on the neighboring areas. And also, we can better understand what is the site response at a specific place to a given earthquake, because we have plenty of earthquakes. We can test, okay, if an earthquake occurs here, what is the amplitude that we're going to expect here? Is it going to be a big deal for the inhabitants and things like that? So having more earthquakes is good for us to do this kind of analysis. Okay, so this was just an example to say we also work with earthquakes. But if we go back to the data and look more carefully of what's happening in the data, we see much more occurring that is not yet really understood. I'm going to show an example. So this is, we're back in 2000s, in early 2000s. This is the Cascadia subduction zone. So it's basically the Western North America. Here you have Seattle. Here somewhere you must have Vancouver. And so basically you have a plate here, which is called the Juan de Fuca plate, that is subducting beneath North America. And if you take several seismic sensors in this area and you plot them, okay, so this is synchronous seismic data collected at several sensors. What you see here is a noise that is quite hard to characterize if you take a single station, but if you look at several stations at the same time, you realize that this noise looks somehow correlated, right? So actually, it's not correlated in phase, but the envelope seems to be correlated. And here the scale is about 10 minutes. And so these kind of signals, we started to observe them because we started also to collect continuous seismic data. Before it was not the case. We only collected waveforms that were chunked around earthquakes in order to not to saturate the servers that deliver the data. So we could not afford collecting the continuous data. At some point, we decided it was okay, it was time. So we collected the continuous data. And we observed that in several places at the same time, around the same date. So they called these kind of signals tremor. And they made the assumption that this, if the same signal is recorded everywhere, it may be due to the same source, right? Hard to locate, hard to define. It's kind of a noise. It spans several frequency bands. So it's not really easy to digest, but it was a first observation. And at the same time, okay, I did not say, but actually we are still in the loading period in this area. So this is occurring during the loading, right? Out of an earthquake. And at the same time, people also started to dive into continuous GPS data. So this is supposed also to show that there is a continuous loading because we are out of an earthquake and the coupling is quite good. But what you see actually is that there are small, backward motion during the loading period of small earthquakes, okay? But it's not as fast as a regular earthquake. It takes actually about a month to slip. So it's the same slip than an earthquake, but an earthquake would be several seconds long. This one occurs on the course of a month. And it seems that it occurs at the same time than tremors that are observed in the seismic data. So we have a new, at that moment, we realized it was kind of a new type of earthquake, very silent because they don't generate seismic waves as we saw before. They radiate some kind of seismic energy that is very hard to understand, and this was a discovery. So many papers were actually made afterwards to understand why these slow slip events occur and why do they occur during tremor episodes. And actually, these events, they can deliver equivalent magnitude earthquakes of about magnitude 7. So these are large events, but they're silent. They don't cause damage. But if you want to improve your seismic cycle, you definitely need to understand how do they occur, what is the frequency of occurrence of these, in order to better quantify what is going to be the next, when is going to be the next earthquake. So there is basically we're we're overestimating the loading. There is much less loading than we thought. And also in addition, so this is a zoom on one single slow slip event in Mexico, equivalent magnitude 7. So it's a large earthquake, but silent. And what you see in this displacement, so GPS data is very noisy because of the atmospheric turbulences. We cannot accurately measure the displacement. But we have seismic data to better time when is going to occur the slow slip. Because if we make the assumption that tremors occur during slow slip, we can time the tremors. And with that, we realize that actually it's not a continuous slip. It's an episodic slip. So if you were to zoom in that, and if you were to denoise it, you would realize that actually within a slow slip event, you have an episodic slip that is faster than the overall slip. So in order to measure accurately the energy release of these events, we need both seismology and geodesy to do a good job. And of course, we still don't know how to define a tremor. So detecting something that we don't know how to define can be tricky, right? We need dense seismic networks to actually detect them or find patterns that look like them. And also, it's super different from a context to another. So it makes the exercise really interesting. And nowadays, we detect them in many places. All around the world in subduction areas. Also on these weird faults. So I was mentioning on the subductions, but you also have continental faults that are transverse faults, like the San Andreas fault. And we discovered also there that we can find tremors and slow slip events. In Japan, it correlates a lot with places with a very dense instrumentation. And for instance, in Chile here, we have a problem, kind of, because we see the slow slip events in the GPS data, but we don't observe the tremors. So we have these kind of things we need to understand in order to model overall these kind of events. Okay, so the last introduction slide. So basically, the community kind of agreed on these kind of events that we can see in GPS and seismic data. Earthquakes, we all agree on that. We can observe them everywhere. And this is a diagram that it's a bit outdated, but it's still also very up to date in a sense. So this is a diagram where you represent the moment, so the energy release of a given event against the duration of this event, okay? So basically a magnitude 7 earthquake here delivers, it occurs on a course of tens to 100 seconds. And there is a scaling law of the regular earthquakes that the smaller it is and the less duration it has along this line here. But if you consider, for instance, tremors, they locate somewhere here, episodic tremors and slow slip events. So they can occur on the course of 1 month, okay? But they deliver magnitude equivalent of magnitude 6.5. And it seems that all these different events that I did not detail, low frequency earthquakes, very low frequency earthquakes that are particular spectra, also slow slip event, they tend to align along this trend here. It's a lot debated, but first order, it works quite well. And so we call these kind of new events slow earthquakes because they have a much different scaling law. So the questions related to that is, in order to make this observation and to let the community agree on that, we had to visually dive into the data. So people screened the data, they monitor the data, they discovered this new kind of event, they proposed a new class, they tried to provide names and so. But in this diagram, we have observational gaps. I mean, you cannot observe some events that would occur here because the instrumentation is not capable of seeing it. So there is probably a lot of events here that we miss. So the question we want to address here is, did we miss something? And how do you test that? How do you automate? How do you use AI to dive into the data automatically and discover new types of data, characterize them, provide definitions of the classes? And thanks to that, can we update this figure and provide a more complete seismic cycle model? So this is basically the motivation. Okay. So the question is, how do you do that? How do you dive into continuous seismic data, find patterns, and try to define them? So this image here in the background, it was published in 2010. It was, to my knowledge, it was one of the first papers that decided to dive into data and train a machine to find whatever pattern without giving an idea of what we're looking for. And they were quite successful, but the computational cost of that was crazy. So it was applied only on like 2 hours of seismic data. It's not scalable. We want to digest 10 years, 20 years of data. So we need to find a better way. Basically, I'm going to speak about machine learning here. There are 2 ways of, so the generic name of this problem is to find classes in the data, so class membership identification. And you have 2 ways of doing that. Either you supervise your algorithm, so you give classes that you know already. This is an earthquake, this is a tremor, and you let a model of a machine learning model try to replicate this. So if you do that, you need labeled data that you provide classes with and that you are going to teach the machine to replicate. And you cannot discover new classes with that, of course, because the machine is going to be limited to the classes you teach. But it's quite straightforward to design. So this is classical AI. We cannot go this way, so we're going to go unsupervised, which means that you're going to look for groups, natural groups in the data, and you need to provide an implicit formulation of your problem, but then you don't need for labels and you can reveal new classes. So this is what we're going to try and do. There are literally tens of papers on that only in seismology, although it was we're 10 years later than 15 years later than the first paper. Few papers try to tackle this kind of issue because it's this implicit formulation. I mean, your result is going to depend a lot on that, so you need to be careful in this formulation. So basically, we're going to do clustering. So this is an example with a two-dimensional data set. You want to find groups in this data set. You have plenty of definition of what clustering is. Depending on that, you will always end up with a result, and you need to interpret your result based on that. So this is an animation with a group of points, and this is a famous algorithm that is trying to partition the data set into different subgroups. The name of this algorithm is K-means, and it's a top-bottom approach. So basically, you look for segments of the data set into smaller subgroups that are more homogeneous. There is another definition that considers looking for similarity between points, and so it's a bottom-up approach where you calculate the similarity between all your points and you group the points like that. Depending on the definition you have from homogeneous and similarity, you will define plenty of algorithms. These are 7 different algorithms applied to 3 different data sets. This is a showcase from a machine learning library that is open source and very easy to use. So you see that depending on the distribution of the points, so for instance, the two-circle problem, you have some algorithm that may be super efficient, some other that may not. So you need, basically the message here is to say you need to have a prior knowledge on your distribution of your data if you want to select the best algorithm. This is something you need to be, you definitely need to have domain experts working with AI experts to find out what's the best approach to your problem. So this is exactly what we've been doing, trying to understand that. And the second challenge is we deal with waveforms. So when you deal with two-dimensional points, it can be okay, you can represent things, you can test different algorithms. Waveform is a high-dimensional object. So imagine that you segment your data into small segments of windows. You can consider this to be a point in an n-dimensional space, n being the number of points of your waveform. And you could evaluate distances for similarities or things like that, like for instance, correlation coefficient. But it's really not efficient to do that because a waveform is highly depending on where exactly is the window. If you have an attenuation due to scattering or radiation pattern, you will change completely the coordinate of this point in the space of waveforms. And so you will probably have a big problem trying to evaluate similarity. So basically, we need a better representation to do that job. We need to transform this waveform into a space where we can do this clustering in a better way. So it seems that actually, it's the big problem that I'm going to show is that one. It's the one I've been working on for the last 4 years. So in order to solve the problem, we use deep learning. So not entering the details, this is a very, very simple scheme of the convolutional neural network. Cats and dogs, I guess everyone is illustrating neural networks like that. So you want to classify images of cats and dogs. Every line here represents a convolution of the image. So basically what you want is that if you give an image of a cat, here you want this value to be close to 1 and this one to be close to 0. So the probability to belong to a given class is delivered by this probability, these likelihoods. So the sum of the two gives 1. And so you want to transform this image into this distribution. And so in order to do that, you will convolve the image here with a filter. You don't know the weights of the filter. This is what you're going to learn, basically. And you also apply a nonlinear function because you can imagine that this function is highly nonlinear. So if you only do convolution, you will not be capable of fitting a nonlinear function. So we have slightly nonlinear functions that are applied to every output of every convolutions. And so what you're learning basically is the weights of this filter that is going to be applied here. You apply the nonlinear function, you apply again convolutions and so on. And in the end, you hope that by training on a lot of images, you will be capable of inferring cats and dogs, and that this model is going to also work on new data. So the problem of that, so this is the way, okay, we have a big problem with this kind of models. It's hard to design. We don't have a mathematical recipe to say you need to design it this way in order to solve this kind of problem. So what people have been doing are these kind of challenges called hackathon, where people are going to develop plenty of models, try and error on many, many data sets. And at some point, they end up with working architecture for a given task. And it's not guaranteed that this model is going to work on another set of data. But for an illustration, this is VGG16. It was the winner of a challenge in 2016 for image classification. And if you look at the filters here, these are the filters that are learned at the first layer. You can see that these filters are sensitive to different patterns in data. It was inferred from data, basically. So directions, maybe also change of colors and things. So, okay. The idea here, the message is to say, there is a French mathematician that in 2014, they decided to say, we don't really need to learn like that. We can replace this filter by some analytical filters. So this is an example with Gabor wavelets. Wavelets, they have similar properties somehow than the filters that you learn directly from data. But if you replace the filter directly with the wavelets, then you get rid of the learning. You can just apply your neural network on that and use this representation instead of the learned one. And so in order to digest the seismic waveform, this is the kind of model we decided to use. So for 1D signal, it's the same. You have your input signal X here. You apply a wavelet transform. You consider applying again, I mean, it's a cascade of wavelet transformation, and this is going to decompose your signal. I have a better illustration here, actually. This is your input waveform. You do the wavelet transform. You end up with what we call a scalogram. Gives you information about time and frequency content of the data. You will again apply another set of wavelets. You obtain a lot of spectrograms. And these scalograms, we apply smoothing function to reduce the amount of details and to stabilize the representation. So this is what we use as a representation. So here I'm going to illustrate my point. Okay, so this is the slide ordering is not good. I'm going to illustrate how we can use that in the specific context of Mexico. So here I'm going to, so Mexico is it's a subduction area that also hosts slow slip events and tremors. But there is a challenge in this context that we have only one GNSS station and one seismic station. And as I said before, in order to do the studies we did before, we need a lot of sensors. So the goal here to use AI is also to be capable of seeing this kind of similar pattern in this subduction context with a few sensors. So the round here is a seismic sensor, and the square here is a GNSS sensor. And the patches that you see here are the location of the large slow slip event that we saw from 2009 till 2017. So this is the GNSS data, one station. So you can see here first two slow slip. This one was missed from this GNSS data. This is a slow slip that actually triggered a large earthquake. So this is an earthquake and an after slip, but it's a much smaller earthquake than the one we saw before. Okay, you can see in the GNSS definitely that the seismic cycle as described before is not working. And what we did, we took 10 years of data, we segmented it into into alpha-hour windows. We calculate the scattering coefficients out of this scattering network I was presenting before. We collect these values that represent the information of the data, okay? We reduce the dimension because it's too highly dimensional and it's hard to work in high dimensions. And from this very low dimensional representation, so basically you have to imagine that this is a vector of 20 values that represent the content of this waveform, okay? Seismic data is 3 components, so actually we give the 3 component data, so north, east, and up. We concatenate all of that, and we have 20 coefficients that are supposed to be fully representing the input data. And if we look for groups, so Sorry, it may be overwhelming, but basically what you see here is the detection rate of the different clusters we inferred automatically from the data. So, and this dendrogram here shows the connection between the different clusters. So you can see that there is a dynamic in the data. You have clusters that are, for instance, a bit quiet, and then you have a sudden increase and a decrease of the detection rate of this cluster. You have clusters that occur, for instance, this one, G1, is occurring specifically at this place, okay, right after a large earthquake that occurred in the area. You have plenty of different histories here. Here you have the detection rate over the course of a day. So this gives you an idea of if a cluster occurs mostly during daytime or not. It can be interesting because seismic sensors are very, very sensitive. You can detect cars, planes, you can detect plenty of things. So it's good also to disentangle between things you're not interested in. And what we're going to look at right now is this cluster E, because it has a specific signature that looks like the one we were going after, which is the tremor detection rate. Okay, so these are okay, you can visualize for every cluster, you can visualize the waveforms that were detected. Here is so you can see that A1 to A6, they contain waveforms that show small duration events, okay? So if you were to zoom here, you would see that these are small earthquakes. Maybe these earthquakes, they last a bit longer than the ones you can see here. Very, very small spikes in the data, small earthquakes and so. So it's interesting to see that actually all the seismicity was kind of gathered into the first branches of this dendrogram. Of course, we test our algorithm on a place where we have a little knowledge, so we can compare with actual catalogs and so, before diving into really unscreened data. So we compared with catalogs of earthquakes that were inferred by the University of Mexico. We can see that most of the earthquakes of the catalog are actually gathered in the first clusters, so it's a good point. Now that we know that what we know already is well collected by the algorithm, we can look at the other clusters. And actually, we also applied this algorithm on another place in Turkey. So we did exactly the same method. What you can see here are the 3 component waveforms of earthquakes. So what you see here is an earthquake. Okay, plenty of earthquakes that come from the same place were collected by the algorithm. And we detected new earthquakes in blue here. And when we try to see if they look like the one that were already cataloged, we see a clear match in the waveforms. So it means that the algorithm is capable of detecting smaller earthquakes than the one we're capable of detecting already today. So this is just to illustrate that when we're going to look at where the earthquakes of the catalog occur in the clusters, we're clearly capable of having way more earthquakes, and this is what this diagram is showing. We detect way more earthquakes than what we had before. But if we want to interpret that, we need also a catalog. So this is the contradiction. We cannot dive directly into the data without any prior knowledge. Okay, and so the second cluster we are interested in here is this cluster E. You see it's a cluster that is kind of episodic. And in the gray area here, we have these slow slip events we were mentioning before detected in GNSS data. So the correlation is not exactly what we expected, right? I mean, people in the literature, they have been saying tremor occur mostly during slow slip events. But in that case, you can see that, for instance, this is a slow slip event here in 2009. Where is E? Here. You have an elevation maybe of the number of tremors, but it's not completely correlated because we have also tremors out of the period of the SSE, of the slow slip event. So anyway, we decided to look and compare with the tremor catalog that was made manually. No, it was, yeah, kind of semi-manual. And so we see that the detection rate, so this is the cumulated detection rate of tremor. You can see this stepwise accumulation of tremors. And you can see that there is a good match between our cluster E and the tremor catalog. So it means that without even defining a tremor, we never said that to the machine, we can detect and separate this contribution, the tremor contribution, and have a good quality result. So it means that we can try and apply this into places, for instance, Chile, where we cannot detect tremors yet. Maybe we should apply that and see if we can detect them. So it's good, but a clustering like that, it's kind of a catalog, right? We can count the number of waveforms that relates to tremor. But we need to do a strong assumption in that is when we cluster a waveform, we need to make the assumption that there is only a single event occurring in that. This is basically when we do the clustering, it's a binary machinery. We cannot have the mixing of different sources within a window. This is because we decided to make the clustering, but before that, as I said, we used a decomposition algorithm to retain only 20 features, 20 descriptors of the waveforms. These are very hard to interpret because these are values that continuously vary between different values. They don't have a clear signification, but we could use them instead of clustering to see if we can compare this representation of the seismic data and the GNSS data. So this is another experiment. So for instance here, I selected this feature here, sorry for the representation, but we can see it's a very spiky feature, and it's a feature that looks much more like, it's much like this cluster here. So we decided to see if we can interpret this feature in terms of tremorness. So we try to get rid of the idea of cataloging events, and maybe we can continuously monitor the amount of tremor we have in the data. And maybe it's a much cleaner description of what's happening than trying to count the events individually. So we consider tremor now as a continuous process rather than a burst of events. And the experiment we decided to try was to see if we could replicate. So this in blue, what you see here is the derivative of the GPS data. So it's not the displacement anymore, but the displacement rate, the velocity. So this is the blue curve, and in orange, what you obtain is what you can reconstruct in the blue curve by considering linear combination of all these features here. So basically, we try to see if we can express the GNSS displacement rate in terms of features of the seismic waveforms. And you can see that there is a reconstruction. It's not perfect, but we have 70% of the GNSS that we can reconstruct out of this representation. What is interesting is that then you can go back to that. Okay, you understand what is the contribution of this representation into the GNSS, and then you can characterize these tremorness features in terms of displacement. So we can estimate things that we could not do properly before, which is magnitude of the tremors, for instance. We can also improve the location of these events because we have a better idea of what they are. Actually, this is what we could call a definition of this kind of event. It's digital. It's not a definition that can hold in every places. But this is a new representation that can be useful to better characterize these kind of events. Okay, maybe I will finish on that other application. So for instance, we did exactly the same thing on seismic data from a place in Germany, in Hamburg. We had several seismic sensors, and this is representing the temperature in Hamburg at this time of the year. So actually, you see that the air temperature, which is represented in blue here, they went way below 0. It was -15 for actually a couple of weeks. And so what people wanted to do at that moment was to investigate what is the thickness of the ground layer that was freezing, just to understand what is the depth of the freezing layer of the ground. So they used the seismometer and thermometers, and we applied the same machinery. We decomposed the data into descriptions of the data, like features. And we tried to see if one feature was correlated with temperature. And it was the case. So actually, the black curve here is the features that correlates the most with the temperature observed with thermometers. So we have a quite good approximation of temperature with a seismometer, although you may say it's a quite expensive thermometer. But it means that we captured something in the wave field, in the seismic wave field, that is sensitive to temperature. It's not, it's not completely straightforward when you think about it. But anyway, you can now try to understand what is the relationship, and you can model it better. What's the relationship between this feature of the seismic wave field and the temperature? And so one way of doing this is to understand what is the ratio between horizontal displacement of the seismometer and vertical displacement of seismometer. Gives you an idea of what is basically the content of the wave field. If you do that the classical way, without having this separation of the different contribution made by this algorithm, if you apply that, you cannot make a difference between a change in the source field and a change in the medium. Because when it's freezing, actually, there is a lot of human activities that are going to stop. So you cannot make a difference if the H/V ratio is going to be due to a change in the human activity. For instance, there is a gravel pit located nearby, the activity of trucks, and so it's supposed to stop when it's freezing. So it's going also to have an impact on that. And if you look closer, you will see also that there is a contribution of weekends and weekdays, and so definitely you have a human impact on that. But if you only recalculate this based on only the feature that was correlated with temperature, you realize that it's so badly, you have to imagine a little bit with me, that you can see the freezing effect only during the time where the temperature goes way below zero, and you're not anymore too much impacted by the human activity. So the message here is that we can actually make a difference with a single sensor between changes that occur due to the sources and due to the medium. This is not supposed to be really easy to do with a single sensor, but we think it's something we can approach because the statistic of occurrence of the human sources is different from the one of the temperature. So yeah, so this is the conclusion. So this algorithm is supposed to dive into data and discover new classes. So the formulation we decided to adopt was this algorithm based on the scattering transform. So this neural network that is based on wavelets. So it's a bit, it's a semi-analytical neural network. It's computationally efficient because you don't have this learning procedure that can take ages, and also that is supposed to work on a lot of data. Here, we want to be capable of both digesting large data sets, but also small ones. If you have a data set that is only for 2-3 days, you can still apply that because no learning is involved. And we applied that into different contexts to observe the capacity of this algorithm, voilà, to find different events and to relate them to what we know already. And so the final goal of that is to implement a better seismic cycle. So thank you for your attention.
Thank you, Léonard. That was really interesting. I think we have a question from yeah.
Thanks. That was really nice. I'm not sure I completely understood the scattering transform and those 20 features that you derived from the waveforms. So the 20 features, there's also a learning part
Yes.
in that, right? So
Yeah,
you do a wavelet transform, you trim the tree somehow to compress the data, but there's still a learning part somewhere, right?
Yes. So the scattering transform delivers basically about a bit more than 1,000 coefficients, because basically, so you have your input signals, you do a given number of wavelet transforms, and you do again another set. So these can grow quite easily to a large number of coefficients. And for every window, we retain only this set of coefficients that is basically averaged over the window. You can apply other kind of pooling, but and this is literally too high dimensional. So in order to go from here to here, plenty of solutions. You can do SVD, ICA, things that are basic and linear. Basic and linear is better for us because we can keep interpretability, but you can also reduce that with a neural network. You can use plenty of methods. So here we applied ICA.
ACA?
Independent component analysis.
Okay.
So we keep interpretability because you can go from here to here. You cannot go from here to here. There is no inverse transform of that because you lose the phase information with the averaging. But already here you have a good interpretability because this is basically spectrum and spectrum of spectrum, so it's quite easy to interpret.
Yeah. Thanks.
Yes, thank you. It is in the same. How do you segment your signal? Because I think it's a tricky point. And second question. Did you look at audio descriptors, because it's a wave and you have spectrum and stuff like that? And so I think there is, to reduce the dimension, you can look at harmonicity, frequency, stuff like that.
Yeah, okay. So segmentation, you mean you can have redundancy if you have a sliding window, for instance, or was it more about...
Yeah, because you say that you average your descriptors on window, and so how do you choose in window, and do you have an overlap or stuff like that?
So we disregard overlap because overlap is making the clustering very messy. If you have redundancy, you can have singularities and you mess up your... So we disregarded that for the moment. We tried to see... So in that case, we don't do average. we do maximum. We keep only the maximum coefficient. So it's nonlinear and it can mix up different events that occur at different frequencies. It's a bit risky, but it gives better results in that case. And the segmentation, we did that without overlap for the moment. We think in order to solve the problem of having overlap, we need to release the constraint of making the assumption that there is one event per window. Then we can better deal with overlap. But it's a tricky question, I agree. And the second one was about, the window width. So in that case, we know that tremors occur, they may have between 5 minutes and 20 minutes duration. So we fix the window at 30 minutes in order to make sure that most tremors are going to be recorded within a window. It can be cut halfway, but because of the maximum pooling, we don't really care. But so we took the windows to ensure that it will contain the largest duration event. As simple as that. And if an event is very small compared to the window duration, we don't really care because the second order scattering coefficients, the ones that look at the scalogram of the envelope, okay, they give you an information about the width of the event inside. So if there is, the dominating event is going to be the one that is better expressed in the coefficients. So if you have a small event compared to the half-hour long window, it may still express, right? Because you have the history of the waveform within the window that is encoded there. And actually, this transform was compared to most audio processing features, like the MEL spectrogram and all these harmonic features. They have good scores when they do audio classification. But we also thought about taking directly the deep learning algorithm that were trained on audio waveforms as a pre-trained model to apply them directly. I'm sure it can lead to very good results also there. The advantage of that is that you can interpret still a bit. I didn't show examples, but you can represent the features and have an idea of where is the energy in terms of durations and frequencies. So it's a good in-between, I would say.
Thanks a lot. Very, very interesting work. I have 3 short and naive questions. The first one is, from the mechanical standpoint, how do you interpret the fact that the source is a point? What happens at that point? Secondly, when you do this classification in high dimension, are there issues in terms of choosing a metric or a norm, and how does that affect? And then lastly, you discussed the monitoring and description. Maybe you open it to it in the last slide. How about predicting? I mean, what can this say, and why is it difficult to predict?
Okay. So the first question, you said when I say a source is a point, you mention earthquakes, or you say you speak about the waveform? Okay. So like for here, for instance. So it's definitely not a point, indeed. For instance, this is probably the most descriptive image of an earthquake, right? An earthquake is definitely a slip that is not localized in space. When we put a star somewhere as a seismologist to say this is where the earthquake occurs, it's usually the initiation of the rupture. You have to imagine that this is a dynamic process. There is a spreading of the rupture on the interface. We put the star at the initiation point most of the time. But then for very small earthquakes, the extent of this slip is so small that we consider it's a point. Does it answer your question? Okay. But of course, it's a lie. Sorry, here?
Yeah. So in a bigger area and bigger slide area north to the star.
Yeah. Oh, yeah. Because the maximum amplitude of the slip is not necessarily at the initiation of the rupture. It can. Okay. So you have to imagine it starts to slip here. So the slip is going to cascade up to this point, and maybe you have a larger slip here because this was more prone to slip than this place, actually. So yes, the initiation of the rupture is not necessarily the largest slip. Yeah. You have to the choice of the metric. So yeah, so high dimension is very bad if you want to calculate metrics because when you grow in high dimensions, you will tend to have more similar distances in many areas of the space. So you need to reduce dimensions in order to evaluate metrics, okay? So we go from a quite high dimensional waveforms in terms of number of points to a high dimensional space, but which is supposed to be stable based on the proofs that were written here, basically. So the qualification of the representation of the waveform through this network is kind of guaranteed to be stable to small deformations and small, shifts in time. So we use this representation to say, okay, now we can apply linear reduction algorithms because it's certain, it's kind of guaranteed that if two dissimilar waveforms are slightly dissimilar, they will find a different representation in this intermediate representation. But still, it's too high dimensional to evaluate metrics. We don't calculate distances here because 1000 dimension is too high. So you will have similar distances between similarly dissimilar events. Sorry. You understand what I mean? So if you have waveforms that are not similar, but you want to evaluate how dissimilar they are, distance is definitely not a good metric in high dimension. By reducing the dimension, you avoid facing these kind of challenges, okay? And here we apply a very simple dimension reduction, which is close to singular value decomposition. So we retain the 20 most relevant correlated features in that, and we keep only that. There we can calculate distances, and what we do is very simple. We do a hierarchical clustering. So we actually normalize the distance between different points by the density of points. So we ensure that if there is a small cluster near a big cluster, we can still make a difference between the two. Otherwise, this distance only is going to fail. We have way more noise samples than earthquake samples, and earthquakes may gather at a small space, whereas the noise is going to be diverse, so we need to accommodate that. The what? Prediction of earthquakes, you mean? Say yeah, so yeah. We can't predict earthquakes, it's a chaotic system. We have to imagine that what we do nowadays to better understand the dynamics of faults is to see not a single fault only, but the system of fault, because you imagine that everything interacts at different scales. So you don't have only the loading that occur on a specific fault, but if the neighboring fault starts to have a slip, it will maybe trigger something locally, maybe it's going to be a slow one, maybe. So prediction is probably out of the reach here. Also, in this specific context of Mexico, we know nowadays that most large earthquakes were triggered by slow slip events. This is a new observation. We need to better understand what is the relationship between slow slip and earthquakes. So I guess what we're doing is more like trying to monitor, to make an inventory of everything we can observe in the data before doing actual statistics and understand if there is a prediction capability or not. This is my best answer to that question.
Investigated preceding events of the preceding events of an earthquake, maybe without understanding why they are occurred. Just the similarity, maybe before, maybe there are some patterns always the same, and without understanding the reason, maybe it could help anyway to give a certain probability of occurrence of an earthquake. Is also considered.
Yes. Oh yeah. But for instance, so this is, in 2014 we had an earthquake in Chile up north, and there was a pattern of 4 shocks. We call them four shocks. So earthquake, we call them a posteriori 4 shocks because we cannot say there are 4 shocks before. And the pattern of 4 shocks was repeated 4 years later. So everyone was like, we should deploy sensors now in order to observe it, and nothing occurred. So the potential of prediction is like 50%. but we lack long duration observations, basically, of course, yes. So maybe there are patterns, because so far all the earthquakes we observed were in different contexts that are hard to compare. But maybe such pattern exists, yes.
Thank you, Leo. Just have a small question about so you decompose everything on, like you make wavelet transforms, essentially. And so does it depend on the wavelet you choose?
Yeah.
Like, how much does it play a role in
Oh, yeah. Okay, how can I illustrate? Well, okay, so at the beginning, what we were doing, we were learning. So, there are plenty of ways of defining a wavelet. So we took a Morlet wavelet or a complex Morlet wavelet, which is probably the simplest to interpret in terms of representation. But at the beginning, what we did, we were learning the wavelet in order to make a small step towards deep learning. Instead of learning completely the full filter as a convolutional network, we were learning the shape of the wavelet to maximize our chance to cluster. But it was unstable. So we applied that on the precursory signal of a landslide, or maybe easier to predict than earthquakes, basically. And so we did that, and we were capable of detecting the precursors, but we were learning the wavelet, yes. Here we impose the wavelet, and the constraint is interpretability. So this is how we choose. But we could try many wavelets indeed.
because I've tried changing the wavelet and seeing if you have the same kind of features.
Well, it depends on the task. When we applied that first, it was on Turkey, and in Turkey we made a test like that. We also test, not a wavelet but a sine so Fourier transform basically, and we saw that there was an improvement by using a Morlet wavelet, but Gabor wavelets and all these different shapes were not delivering much different results. I think actually the step that is taking the lead is this one. Afterwards, because okay, you can have different wavelets here. The representation will change for sure, but the latent variables here, they're quite stable because we retain only 20 of them. So it's and if you go on volcanoes, I didn't show, but volcanoes you cannot compress. Here, 20 features express 95% of that, so it's a lot of redundancy. In volcanoes, you need 200 of them to represent that. It means that volcanic systems are probably much more diverse, and there's more richness in the signal than in subduction contexts. So there, maybe the wavelet shape is better to consider. Yeah.
Questions?